All right, for 2-5, we're going to be working with complex numbers and roots. So a complex number is a number that's made up of a real and imaginary parts. So you'll see an example here where we just pick up where we left off with from 2.3 and 2.4, where you're finding the zeros, and then we'll graph. So remember, if you want to find the zeros, we set the function equal to 0, and then we would solve. So x squared plus 1 is not factorable. We subtract the 1 over, we get -1 equals x squared. When we take the square root of both sides, we get x equals plus or minus the square root of -1, okay? And we all know that we can't take the square root of a negative, right? There's no number multiplied by itself that will get us a negative. That's why we have imaginary roots. All right, if we were to go graph this function, we know the vertex is at 0, 1. It's in vertex form. And then we could graph using our parent function values, -2, -1, 0, 1, and 2, 4, 1, 0, 1, and 4, and just graph those from this point. So -1, 1, +1, 1, 2, 4. Remember, you graph those from the vertex if you're graphing in vertex form. And we got something like this, okay? And then hopefully you can see why there's no real zeros. It's because the graph is not crossing the x-axis, right? So there are no x-intercepts or zeros, which means there's no real roots or solutions to this function. Okay, so instead, we call these imaginary roots. We don't just stop and say, okay, there's nothing we can solve for here. Instead, we have something called imaginary roots. And those imaginary roots are roots when the quadratic function does not cross the x-axis, okay? An imaginary number, we just use the letter I. It's just the square root of a negative number. Right, and your most basic imaginary or your most standard imaginary number we're going to use a lot is the square root of -1. And the square root of -1 we just write as I, okay? So anytime we have the square root of a negative, we can just write this as I. It represents an imaginary number, the square root of a negative. All right, so let's try a couple of examples here where we're not finding the square root of just -1. If we were finding the square root of -2, or we were finding the square root of -12. Let's work these both out here. For the square root of -2, you can just break this up and write it as root -1 times root 2. And then hopefully you can see this square root of -1 just comes out as I, and you're left with root 2. There's nothing we can do to simplify root 2. So the square root of -2 just gets us I root 2. Let's try root 12. Remember, you can always just take out the negative as I if you'd like, or you can write this as root -1 times root 12, and you can really see where that imaginary or I came from. So there's our I. Imaginary number means we had a negative underneath our radical. And then you can't forget for 12. Remember, for 12, we need to pull out perfect squares because 4 is a perfect square, and you can take out 2, right? You can rewrite the root 12 as root 4 times root 3, and root 4 is a perfect square. So when we simplify this all the way down, we get 2I root 3, okay? So imaginary numbers can be written in the form write that can be written in the form bi, where b is the real number and I is the imaginary number, right? And these all make up a complex number. So a complex number is just a number, and we're going to get down there to our definition in just a sec, a number that's made up of real and imaginary parts. Okay. One last example I'd like to work out here is when we take the square, and we take the square of a negative. Okay, so let's work that example out. We had something like this. Root -1 squared. Hopefully you remember that radicals and squaring, they just eliminate each other. But if you didn't, or we were unfamiliar with that, we could rewrite this as root -1 times root -1, which gets us I times I, which equals I squared. And that should tell you that I squared is always going to equal -1. Okay, so there's another property of our imaginary numbers. I squared will always equal -1. What if we had the square root of -20 squared? Right, this is not going to equal -1 because you have root 20. Instead, your radicals are just going to eliminate, right? We have root -20 times root -20, which gets us I root 20 times I root 20. You're going to see these just eliminate, and you're left with just -20. Okay. Just more examples of imaginary numbers and simplifying. So a complex number are all those solutions you just found. A number that can be written in the form a plus or minus bi. Okay, and you had plenty of examples up above. Complex numbers can have only imaginary parts. They can have imaginary and real parts, but I is a complex number. 3i is a complex number. -5i. And then you could have something like 12 minus I, or we could have 1/2 minus I root 3. We just put our radical after. These are all examples of complex numbers, and you're going to see more examples like that as we simplify some of these down below. Okay, so let's go ahead and do that. Let's work out these examples where we're simplifying these radical expressions and pulling out I as our root -1. Okay, let's try number 3 together, and then I'll let you work out these examples on your own. Okay, or sorry, number 1. So we have a 3 out in front. For our -16, if you want, you can write it as -1 times root 16. Hopefully you can see you have 3i here. Pull out I for your root -1. 16 is a perfect square, so this is going to simplify down to 12i. Let's try one more for 2. For 75, again, if you want to write it as -1 times root 75, or maybe anytime you guys see a negative underneath your radical, you just want to pull out the I right away and write it as -I times root 75. And then don't forget 75, you need to take out perfect squares if you have any. 25 and 3, 25 is a perfect square, so this comes out as -5i root 3. Right, try those last 2 examples on your own, 3 and 4. We'll see what you get when you are finished. Number 3, your solution should have been -I root 7. Number 4, your solution should have been -8i root 6. Okay, you were going to pull out 2 pairs of 2s. There's 2 perfect squares, and 2 times 2 times 2 gets you 8. There's a negative out in front on both because those 2 numbers in front were already negative. Great. Let's continue, and now let's find some zeros of functions. We can have complex numbers as zeros or as imaginary roots. So let's do that down here. Find the zeros for number 1. You would do the same thing. Set your function equal to 0. We can't factor, otherwise we would have real roots, so we subtract our 75 over. And start isolating your variable. We get negative 25 equals x squared. We're going to be taking the square root of both sides of an equation, so we're going to have plus or minus. And we have a negative underneath our radical, so our two non-real zeros or non-real solutions would be plus or minus 5i. What's that going to look like on a graph? Well, it's going to be a parabola that's not crossing the x-axis. It's going to look something like this, all the way up at 75. Okay, let's try 2. Oh shoot, hopefully you notice on 2 that there are no factors of 5 that add up to negative 2. So if you can't factor, we spent a homework on this and the whole lesson, we need to complete the square. Can't forget completing the square. So we move our 5 over, get our x terms on the same side. Right, and then we want to add b over 2 squared to both sides, which in this case would be 1. Half of 2 is 1 and 1 squared is 1. This factors to x minus 1 squared equals negative 4. Take the square root of both sides. We get x minus 1 equals plus or minus 2i. And then add your 1 to the other side. We have 1 plus or minus 2i is our solution. All right, why don't you try 3? And remember, those are two non-real solutions, right? 1 plus 2i and 1 minus 2i. Two non-real solutions, or zeros, or roots. Okay, why don't you try 3? You're going to have 2 non-real. You're going to need to complete the square because there's no factors of 35 that add up to 10. Okay. All right, go ahead and give this a shot. After setting this function equal to 0 and moving the 35 over, oops, you are going to add 25 to both sides. Half of 10 squared is 25. This factors down to x plus 5 squared equals negative 10. And we square root both sides. Plus or minus, there's nothing you can take out here other than the negative, so you get plus or minus I root 10. And then subtract your 5 over. We have negative 5 plus or minus I root 10. All right. Same thing applies when we're finding the roots of equations, right? You can have non-real roots. For number 1, we would move our 48 over. Take the square root of both sides. You're going to have a plus or minus. For 48, make your factor tree. 8 and 6, 4 and 2, 3 and 2. So you have 2 perfect squares, right? You have 2 4s, so those come out as 2 times 2, which is 4. You need to take out your I for your negative root. And we're left with 3 underneath. 2 non-real solutions. Hey, why don't you try 2 and 3 on your own, and we'll work those out when you are done. For number 2, after you divide your 5 over, 5 goes into 100 20 times, so it goes into 90 18 times. So we had x squared equals negative 18. Take the square root of both sides, and you're going to get x equals plus or minus. I don't think we can take anything out of, oh yeah, we can. We have a pair of 3's we can take out, so plus or minus 3i root 2. For number 3, I believe you needed to solve by completing the square, right? You can check to see if you can factor. I don't think there were any factors of 18 that add up to 6, right? 9 and 2, 6 and 3, those weren't going to work, so you're going to move that 18 back over. Sorry, negative 18. And then we are going to complete the square. Half of 6 squared would be 9. So we get x plus 3 squared equals negative 9. When we square root both sides, we get x plus 3 equals plus or minus 3i. And then move your 3 over. Negative 3 plus or minus 3i. So hopefully you noticed on every single example here of finding the roots, finding the zeros, whenever they were non-real roots, you were always going to have two solutions because of this plus or minus. And that's what a complex conjugate is. It's when the real parts of a complex number are equal, okay? So if I wrote this complex conjugate as two solutions, it would be negative 3 plus 3i and negative 3 minus 3i. Hopefully you can see that the real parts are equal, negative 3 and negative 3, while the imaginary parts are the opposite. Okay, so it's good to remember that you will always, complex solutions always come in pairs. Complex solutions come in conjugate pairs. So there will always be two solutions when they're non-real. Right? If A plus BI is a solution, then A minus BI is also a solution. So this last piece here, if you're asked to find the complex conjugate, and remember, sorry, something else we should have mentioned, in standard form for complex numbers, standard form is always A plus BI, so the real part comes first. Well, if you're looking at number 1, not written in standard form yet, right? Standard form should be negative 15 plus 2i. If we want the conjugate, you would just have the opposite imaginary part. So the conjugate of 2i minus 15 would be negative 15 minus 2i, just the opposite. The real part stays the same, right? Negative 15 stays the same. How about for 2? The conjugate would be negative root 3, real part stays the same, root 3 minus I. Imaginary part becomes the opposite. How about 3? You guys go ahead and try 3. Write the conjugate, the complex conjugate of 6 minus I root 2. Should be 6 plus I root 2. Okay. So just keep in mind, whenever you're finding the solution and you have a non-real solution, like all of these examples, 1, 2, and 3, you should have two solutions, plus or minus, where the imaginary parts are the opposites. Real parts are the same. And you had the same up here. All right, complex numbers. When your quadratic function does not cross the x-axis, you have imaginary roots or imaginary solutions. Okay, we don't just write no solutions. You can keep solving by taking out that imaginary number. Get started on the homework, and I'll answer any questions.